what is calculus 3, multivariable calculus? Well, it is just calculus in more dimensions. So whatever we did with functions of one variable, such as f of x, and graphs and tangent lines and so on, we're going to try to do that with functions of several variables. So for example, if I have a function that the values, z values, depend on two different variables, x and y, then I'm going to draw graphs to represent the values of that function. Just like in one variable, if I started with a value x naught, then I can evaluate at f of x naught, and then that is going to give me a point in the graph, point x naught, f of x naught. Just like that, with a function of two variables, I can pick two different values, x naught and y naught, and that will have a value, f of x naught, y naught, and that will give me a point in the graph, and the graph point has coordinates in 3 dimensions, x naught, y naught, f of x naught, y naught. And now what else can we do with these functions? Well, just everything that we did with one variable. The very first we did was try to understand the growth behaviors, or the rate of change of a function, and we did that by computing derivatives. The point of the derivative was to find the tangent line at a given point. So that tangent line, the slope, is the derivative at that point. And now at that point in particular, we're going to have, well, now I can look at different directions to see how the function is growing. It's growing like this in this direction, it's growing like this in this direction, and so on. And moreover, I can in fact do something new, which is not just see how it grows in different directions. In fact, I have infinitely many directions to pick from, but I can also pick what we call the tangent plane, not just a tangent line, but a tangent plane at that point. And we're going to be able to determine the equations, like we determined here the equation of a tangent line. The first thing we're going to try to do is to determine the equation of a tangent plane. In order to compute the equation of a plane, we're going to need derivatives. So one thing we're going to need to learn is how to take what we call partial derivatives. This function, I can take a derivative with respect to x, treating y as a constant, or I can take a derivative with respect to y, treating x as a constant, and many other types of derivatives that would indicate slopes in different directions, not just the x direction or the y direction. And those derivatives are going to allow me to compute tangent planes, but also they will also allow me to compute things like local maxima and minima. Remember that we use derivatives to figure out when the slope was 0 in a graph and find out a local max in this case. And we can do the same thing here, but of course in more dimensions things get more interesting, because if I go in this direction, then I see that there is what I would say is a local max, but if I go in this direction, I actually get a saddle point. So you see that, well, it does look like some sort of saddle right there. And we'll analyze, looking at several types of derivatives, what kind of critical point we get in these 3-dimensional graphs. Now, we also spent a lot of time in Calculus 1 finding areas. So if we look at 2 points A and B, an interval A and B, then we computed the area under a graph. And we can do exactly the same thing here, except that now the regions where we're going to find areas above those regions get a lot more interesting. So for example, here I can pick just a square like this, and then look for the entire volume under the graph and above that square. But I could have picked all the regions and then look for the volume above some more complicated regions, and we will do that also. Last, we are also interested in what we call, well, lengths. So for example, I can pick some direction in here and then look for the length of this line, this path on the surface. That's what we call a line integral, and then we can pick different paths and compute the lengths along those paths. Those are going to call line integrals, and at the end of the course we will see that line integrals have like this very surprising connection with areas. So we will see things like Green's theorem that tells you that if you have a closed shape, you have a curve that maybe it's what we call a parametric curve. We will learn also about parametric curves, and it's a closed curve. Then there are interesting relationships between the length of the curve and the area that it encloses. And similarly, we will see there are three-dimensional analogs, and the volume of a sphere, for example, will be related also to the surface area. And there are theorems that relate integrals that have to do with the surface with integrals that have to do with the volume that is enclosed by a shape. So we will see some of those, and these are just some of the things one sees during a multivariable calculus class, and I'm very excited to teach all of this.